Welcome to the problem solving session of basic electrical circuits. And today we will be discussing the current assignments week 6 problems that were unsolved in the previous session. And apart from that, we will also look at a few week 7 practice problems. So let's start it. Now we have we will start with the week 6 current assignments question. So we have the following question first. Now, what we are supposed to do in this is we are supposed to find the current that is flowing through the current that is flowing
Sir,
through.
share your screen, sir.
Oh, sorry. So we are supposed to find the current that is flowing through the 20 ohm resistor. Now, for this, first of all, we can make sure that the questions we can do a sanity check in this question that there is no problem in this question. So for that, we must see that in this complete network, whatever current is flowing in must be equal to the current that is flowing out. So the 5 ampere current is flowing inside this network, and 3 ampere current is flowing through node B, and 2 ampere current is flowing through node D. So the total current that is flowing inside the network is equal to the current that is flowing out the network. So the question is correct. Now, to find the current that is flowing through ISC, what we will do is let's consider the current that is flowing in the 30 ohm branch and the 20 ohm branch to be I1 and I2 respectively. So if we apply the KCL at node N1, we get this equation that is equal to I1 plus ISC plus I2 is equal to 5. And then the other two, now we must be careful that we don't repeat the equations, because let's say the other equation that we try to derive is from here. Now let's say we apply the KCL at this node. I1 is coming in this node. 3 ampere is going out of this node. Then I1 minus 3 will be flowing through this 10 ohm branch. Similarly, I2 minus 2 will be flowing through this 20 ohm branch. Now, let's say we try to apply the KCL at this node, then again, what we end up with is ISC plus I1 minus 3 plus I2 minus 2 is equal to 0. That means ISC plus I1 plus I2 is equal to 5. So we don't get any new information, and this equation is pretty much useless if we need to find out the current. So what we need to do is, so now we can observe that the 20 ohm branch and the voltage developed across this 20 ohm branch will be equal to the voltage developed across the 30 ohm branch plus the voltage developed across the 10 ohm branch. So using that, we can write another equation that is 20 times ISC is equal to 30 times I1, that is the voltage developed across the 30 ohm branch, and 10 times I1 minus 3, that is the voltage developed across the 10 ohm branch. On resolving this, we get the following equation, that is 0.5 times ISC plus 0.75 is equal to I1. Now the second equation, again we can do the same exercise across this 20 ohm branch and these two branches over here. So from there we get a relationship between ISC and I2. Now we have I1 in terms of ISC, we have I2 in terms of ISC. If we substitute these two equations in equation 1, we get an equation that is completely in terms of ISC, and from there we can find the value of ISC as equal to 1.625. Any doubt in this?
Yeah, correct, sir. Your answer is correct.
Okay, so let's move to the next unsolved question. Now, in this question, we need to find the power that the maximum power that can be transferred to the resistor R. So, all the people in the meet, have you guys tried this question?
Yes.
Uh, Karan Kumar, can you have you tried this? Okay, so let's go about it. It's a little bit tricky than what conventionally you have learned in the maximum power transfer theorem. So, first of all, if you try to calculate the Thevenin equivalent of the uh, the network at the right at the left of this resistance. So, if you try to do so, what you get is so you de-energize all the independent sources. You short the 4-volt voltage source. You open the 3 ampere current source. Now, in this case, what you have over here is the voltage developed across this 2 ohm resistor is getting. Uh, can you guys please turn off your mic unless and until there is some doubt? Thank you. So, what we have over here is dependent voltage source, a voltage dependent voltage source, and a resistor over here. So, and if we apply a test current into this node, we get V naught that is flowing through V naught is as equal to 2 IT, as the IT is the current that flows through all the nodes in this branch, and hence VT, that is the test voltage developed at the output of this network, is 2 IT minus 4 IT. So this minus 4 IT is due to this dependent voltage source over here. And now we get RTH equal to minus 2. So we cannot realize, using a passive resistor, we cannot realize a negative resistance. So what will be the uh, solution for this is, let's go back to again the basics of maximum power transfer theorem. So what we have over here is, let's say we have a equivalent of any general network with a voltage V and some output resistance R. So in that case, the power that is transferred to the load resistance RL is uh, the voltage developed across it times square into 1 by RL, that is V square by R. So that boils down to this expression that is a function of, so basically we have P as a function of RL. Now, if we try to plot this function across, if we try to plot P across RL, uh, when the resistance when the source resistance is positive, in this case we get an increasing function at the first, then we have a maxima at RL equal to R, and there the power transfer is V square by 4, and it is maximum, and then again it drops down to 0 as RL tends to infinity. But in the case if R is less than 0, that is R is negative. Now again we have to start our curve from R equal to 0 itself, and the reason is we cannot realize negative resistances. So what we have is since at when this curve reaches RL equal to R, our denominator goes to 0, and the power that is being delivered to this resistor goes to infinite, and then again after that it starts falling gradually to 0 as RL tends to infinity. So maximum power that can be transferred in this case is infinite and not b square by 4. So what is exactly happening in this is, basically the load resistance is canceling the source resistance, and we are getting a short circuit across a voltage source, and we are getting infinite current when we have RL equal to R. We have this kind of situation that infinite power is being transferred. Now, this can be practically seen in the circuits with positive feedback and some nonlinear elements such as gun diode that for a certain period of time we have a negative resistance. And in the practical application of these negative resistance is basically in oscillators. So what we want in oscillators is a positive feedback, so that what the concept of oscillator is that it should be able to give you uh, some power at some frequency without any input source. Basically, uh, the efficiency. Input is zero and power output is some particular value. So power transfer is basically infinite in this case. So that's how oscillators work. So like under certain circumstances, we can we can put some huge amplifier in positive feedback and generate these positive resistances. Any doubt in this?
No, understood.
Okay, so let's move to another problem. So in this problem, what we have is so we have two cases. First of all, there is a network, and that network is connected to passive resistance that is R, and it is said that in this case, the power consumed by this resistance R is P watts. And then what is asked in this question is that if a identical network is connected in parallel to this thing, then what will be the power that is being consumed by this resistance? So we have four options: equal to P, equal to 4P, between P and 4P, and equal to zero point 0.5P. Now, since let's consider the general Thevenin equivalent of this network. So what we will have is we will have a voltage source, and in parallel to it, we will have a resistance R1. So in this case, the P that we will have is the V square I square R. The P we can write as I square R. So I is basically V1 by R1 plus R times squared into R, that we have as the power that is being consumed. Now, when we have two identical Thevenin equivalents connected in parallel, so we discussed in the previous doubt solving session, tutorial session, that like if we have this kind of multiple voltage source with non-ideal with non-zero series resistance in parallel, so we the equivalent voltage, the equivalent circuit we can write as V1 R2 plus V2 R1 upon R1 plus R2, and the resistance that comes in series is R1 parallel R2. So in this particular case, since we have V1s are identical and we have identical R1s, so the R1 parallel R2 will become R1 by 2, and the V1 and from this equation, the voltage source will remain as V1. So power 2 that we get is 2 V1 by, sorry, yeah, it is correct. So this is what we get as the power in the second case. Now let's consider extreme cases. Let's say, for example, when we have the R1, that is the source resistance of this particular network is much smaller than R. That means what we have over here is we have a voltage source V1, then we have a R1, then we have again an R in series, and since this resistance is much smaller than this resistance, so this can be neglected, and we can have a short circuit over here also. So in this case, this is a case of an ideal voltage source scenario. So in this case, P1 is approximately equal to since R1 is much smaller, we can neglect it in denominator. So P1 is approximately equal to V1 square by R. And again, since here also R1 can be neglected. So P1 is again P2 is again equal to V1 square by R. So P2 is same as the previous case. What is exactly happening is you are connecting two ideal and identical voltage sources in parallel. So that basically doesn't changes anything in the circuit, because still you have voltage of V1 across this resistance. So uh, the power that is being consumed by this resistance is same as the previous case. Now, the other case is that we have R1 is much greater than R. Now, this is a case of ideal current source. So, let's say, so till now we have considered the Thevenin equivalent. So, if we convert it into a Norton equivalent, we will have a current source that is I equal to V1 by R1, and a resistance R1 in parallel to this. However, since this resistance is much larger than R, so this resistance can be neglected, and what we have over here is an ideal current source connected with a resistor. So like equation wise, if you see what we have is we can neglect R in this case. So we have power as V1 by R1 whole square times R, and in second case we have since it is R1 by 2 in this case, so it becomes 4P. And intuitively, if we have to see it, so what we have is, now what we are doing is connecting two ideal current sources in parallel to each other. So the current that is flowing through this resistor doubles. So power that is being consumed by this resistor becomes 4P. So so now what will happen is whatever power that is being consumed in the second case will be between these two extreme cases, that is either P or 4P. So the answer is C part, that is between P and 4P. Any doubt in this?
No, already I solved the problem. Same answer. I'm also ready.
Okay.
Understand?
So now let's
Uh,
move to,
Sir, this problem probably I got 0.88. I have a doubt on this problem. Please solve this.
yeah. So we will get to it. So we must be so okay. A little bit terminology you have to decipher from what. Absorbed by the load. The load, it should have been mentioned that the load resistance is RL. So the find the value of R that such that maximum power is absorbed by the load. So till now the maximum power transfer theorem that we have studied depends on like in that case we assume that the source resistance and the Thevenin voltage of the network on the left is fixed, and we have a varying load resistance, and then we say that okay, for a load resistance equal to the RTH we have maximum power transfer theorem. However, in this case, the load resistance is fixed, but the overall, because of this varying R, the overall source resistance of this complete Thevenin equivalent will be varying. So if we look at this way, so again, in conventional case, as I told, we have the voltage developed across load is a function of RL, and if we write the relation between P and RL, so what we have is a function that peaks at R equal to RL equal to R equivalent, and then drops down. So the maximum power transfer happens over here. Now, in the case that is mentioned in the problem, what we have over here is we have an R equivalent for rest of the network, then an R in parallel with RL. So in this case, if we try to find the voltage of voltage across this load, that will be basically uh, consider this as R parallel RL, and what we have now is that since we have R parallel RL, so by using that, using the voltage division, we find the voltage developed across this load. So this is what we get over here. uh, that is V into R into RL divided by R equivalent into R plus RL plus R into RL. Now, if we try to simplify it, we get it in the following way. That is VL equal to V by R equivalent times 1 by RL plus 1 by R plus 1. And the power that will be delivered to the load in this case will be VL square by RL. So that will be equal to the voltage developed times square by RL. Now, if you try to plot the power versus R, because since RL in this case is fixed, R is varying. So what you get is a monotonically increasing function that saturates at the value that is V square by V square into RL divided by R equivalent plus RL whole square. And that happens when this term goes to zero. That means R goes to infinity. So, like the maximum power transfer in this case happens when like the R that is being posed by the thing goes to infinity. So, this is how you needed to solve this question.
Okay,
Is
sir.
it clear?
Actually, yeah, it's clear now. I solved through the star delta conversion, and finally I reduced it. I got 0.88. That's why I asked.
Yeah, yeah, yeah. That's what you are solving in that case is the maximum power delivered to this
Oh,
resistance.
okay.
Yeah.
Hmm.
And asked in the question is maximum power delivered to the load resistance. So yeah. So let's move to the next question. So we have a bunch of statements, and we need to we need to tell whether which of the following statements are correct. So uh, what we have is for a network consisting of resistors and independent sources only, it is desired to obtain Thevenin or Norton equivalent across a load which is in series with an ideal current source. So consider the following statement. Norton equivalent of this terminal is not feasible. Norton equivalent of the circuit exists and it is simply equal to the current source only. And Thevenin equivalent Thevenin equivalent circuit across this terminal is not feasible. Now, if you try to draw what is mentioned in this statement, you will get the following circuit diagram. So you have a big network, let's call it N, and then from in that network you have a branch in which you have an ideal current source, and in series to that you have some resistance RL. And what you need to do is you need to find the Norton equivalent across the terminals of RL, or Norton or Thevenin equivalent across the terminals of RL. So for Norton equivalent, what you will do is you will short circuit this branch, and once you short circuit this branch, since there is some current source I naught flowing through this branch, the same current source will flow through the terminals of this particular uh, uh, resistor element. So IN will be equal to I naught. So the second statement that Norton equivalent exists, and it is simply equal to the current source. So this statement is correct. Now, the second part, if you try to open circuit this, now this is not possible because you cannot open circuit anything in the a series of an ideal current source. So, Norton equivalent of this circuit is not feasible. So, the correct answers are the correct statements are statement 2 and 3. So, yeah, any doubt in this?
No. It's clear.
Yeah. So, okay, now I believe that the rest of the questions were solved in the tutorial session conducted yesterday. So we will solve a few questions based on present week's material. So first of all, we will go with the question that okay, we need to find the Z matrix of this uh, circuit that is given over here. So,
I have few
uh,
doubts on assignment 7 in the question paper itself.
uh, but assignment 7 actually the deadline has not passed. So,
Deadline is okay. That is okay. Question itself, some mistakes will be there. I
Okay.
if I passed through discussion forum, there is no answer. That's why I'm asking now itself. Some is whether it is a typographical mistake or concept wise any
Okay.
mistake
So,
will.
can you share your screen and point out the questions?
I will try it. We'll see. No, I already marked the answers.
Just a minute. Let me try it out. Share. Um, so assignment 7. Yeah. Can you hear me? Hello. Am I audible?
You are audible. See the first question answers, especially first A answer, first one. Fourth answer should be ZB plus ZAB should has to come.
Okay. I will. Currently, I have not gone through these questions. I will mark
No,
your doubt. I will
yeah, yeah. First question.
work on it.
Okay,
Yeah.
sir. Okay. Then again another one more.
So, what you have is
Uh,
first question.
for
You feel there is a doubt.
that options which is given, one of the option is it should at least match. So out of this four, none of them thing match it, and only slight mistake will be there. So first option, fourth Z22 will be ZB plus ZAB has to come. First option
Z22 will be
ZB plus
okay. The
that has to
plus
come.
will come.
Yeah, ZB plus ZAB will come. Then go to 10th question.
So in first question, none of the options is matching,
Yeah,
and now in tenth question we have
10th question is
yeah.
you give V2 and I1, but you ask the answer is V2 by V1. It should be V2 by I1 in this particular
So
circuit. In this particular circuit, it is V2 by I1 has to come. Question
okay,
it is
so
asked. So they
uh,
asked V2 by V1. I tried it. What are the answers which is given is it is exactly matches only for V2 by I1 only.
V2 by I. Okay.
Here it is asked is V2 by V1 is asked. I am telling is V2 by I1.
Okay.
One of the answer
So
will match.
either A or C will.
Any one
I.
answer will match with V2 with I1. So
Okay.
diagram also
So
it is given between V2 and I1 only. So but it is asked is V2 to V1.
okay. So fine. I will work through these problems and let the team intimate the team about this.
No problem, sir. Remaining everything, every answers I got.
Okay. Fine. So, okay, we will look at this. So, for now, let me complete all the questions that I have got for today. So, we have, first of all, we have a question that in which we need to find the Z matrix for this particular problem. So, to find the Z matrix, again, for the Z matrix, the equations we have is V1 is equal to Z11 times I1 plus Z12 times I2, and V2 is equal to Z21 times I1 plus Z22 times I2. So, what we can do is we can open circuit the first node and put I1 equal to 0. From there, we will get the values as V1 by I1 is equal to Z12 and V2 by I2 is equal to Z22. And similarly, for the next node, for if we open circuit the other node, we will get the values of V1 by I1 as Z11 and V2 by I1 as Z21. So on open circuiting the first node, what we have is we apply a voltage, a current source of I2 at the node 2, at the port 2. So from there, we get the value of Z22. So from in this loop we have V2 is equal to 2 kilo ohms times I2. So Z22 comes as 2000, and in the other node, since this is a current controlled voltage source, so we have V1 is equal to minus of 20 times I2, and no voltage will be developed across this 5 kilo ohm resistor because it is an open circuit. So Z12 we get as minus 20. And similarly, if we try to do the same for the other nodes, so uh, we apply a current source at the port 1, and we get V1 is equal to 5 kilo ohms times I1. So we have Z11 as 5000, that is 5 kilo ohms. And since this current controlled voltage source has a gain of unity, so we have V2 is equal to I1, and so Z21 we get as 1. So the overall Z matrix looks as follows. So we have 5000 minus 21 and 2000. So this is how we can solve these kind of questions. Similarly, let's try for a Y parameter question. So in Y parameter, what we have is we have I1 is equal to Y11 times V1 plus Y12 times V2, and I2 is equal to Y21 times V1 plus Y22 times V2. Now in the circuit, what we need to see is again, if we put V2 equal to 0, that means short this the second port. We get Y11 as V1 I1 by V1 and Y21 as I2 by V1. And similarly, if we short the first port, we get Y12 as I1 by V2 and Y22 as I2 by V2. So what we have over here is shorting the port one. This 3 kilo ohm resistance becomes useless, and since this is a voltage controlled current source dependent on V2, and since V2 is zero, so the current that will be flowing in this branch would be zero, and this can be open circuited. So what we have is a 12 kilo ohm and 12 kilo ohm resistances in parallel. So I1 by V1 is basically 1 by 6 kilo ohms, and I2 by V1 is the current flowing in this node in this 12 kilo ohm branch. Now, what you need to see is you need to take care of the directions that you
The
have
screen
for
is
this.
not visible. Screen is not visible.
Oh, wait a second. Mm,
Share that.
Start. Just a minute.
Okay. Yeah, no,
It is
yeah,
visible
yeah,
now, I
yeah,
guess.
yeah. Now is visible. Visible.
Okay,
Visible, sir.
so let's start again with the first problem. So what we needed to do was we needed to find the Z matrix for a two-port network given in the question. So to find the Z matrix, what we do is we have the equations regarding the equations relating I2 and V1 are as follows. That is V1 is equal to Z11 times I1 plus Z12 times I2, and V2 is equal to Z21 times I1 plus Z22 times I2. If we so what we have to do is if we open circuit the first node, that is I1 equal to 0, what we get is V1 by I2 as Z12 and V2 by I2 as Z22. So similarly, if we open circuit the second node, we get V1 by I1 as Z11 and V2 by I1 as Z21. So in the first node, if in the first case, if we see, we open circuit the first node. So in this case, and apply a, current ideal current source at the second port. So in this loop, we have V2 as equal to 2 kilo ohms times I2, and because of that, we have Z22 as V2 by I2 as 2000, and similarly now V1 is coming from current controlled voltage source. So since no voltage is developed across this 5 kilo ohm resistance, so V1 is equal to minus of 20 I1. So Z12 comes as minus 20. Similarly, for the second part, that is to find Z11 and Z21, we open circuit the second port and apply a current source in the first port. So here we have again V1 is equal to 5 kilo ohms times I1. That means Z11 comes as 5,000, and this current controlled voltage source has a gain of unity. So and no voltage is developed across this 2 kilo ohm resistance. So we have V2 equal to I1. So Z21 comes as 1. So this is the Z matrix that we get: 5,000 minus 20, 1, and 2,000. So now a similar concept can be applied for finding Y parameter questions, Y parameters. So let's consider this network, and we try to find the Y parameter. So for Y parameter, we have I1 equal to Y11 times V1 plus Y12 times V2, and I2 equal to Y21 times V1 plus Y22 times V2. So if we put V2 equal to 0, that is we short circuit this node. So in previous case, we were open circuiting the no, the ports that for which open circuiting the ports for respective cases. For finding Y parameters, we short circuit the port so that the voltage developed across them becomes 0. So if we short circuit the port 2, we get Y11 as I1 by V1 and Y21 as I2 by V1. So what we have over here is the voltage source V1 is connected. So in this case, this 3 kilo ohm resistance will not come into picture, and this point since this is a voltage controlled current source and V2 is 0, so this also becomes open circuited. So we have two 12 kilo ohm branches in parallel, and so from there we get I1 by V1, that is the current flowing directly from this voltage source, is 1 by 6 kilo ohms, that is Y11, and I2 by V1 is the current that flows in this branch is in the opposite direction of what we consider as I2. So we get a negative sign, and it is minus 1 by 12 kilo ohms. Similarly, for the other port, we short circuit V1, and we get V1 equal to 0. So in this case, since no voltage is developed across this complete branch, so so this V1 is basically in parallel to this 12 kilo ohm current source, 12 kilo ohm resistance. What we have is uh, 3 kilo ohms and this 12 kilo ohm are in parallel to each other. So I2 by V2, that is Y22, will be parallel combination of these two. However, I1, what I1 will be now, since a current of 1 by 12 kilo ohms, V1 by 12, V2 by 12 kilo ohms is flowing in this direction, and a current is being pulled out because of this voltage controlled current source in the opposite direction. So I1 that will be developed will be 1 by 4 minus 1 by 12K, and this 12K can be neglected as this will be a much smaller quantity than 1 by 4. So Y21 is approximately equal to 1 by 4. So this is how you can handle the questions with to find Z parameters and Y parameters. Now, a slightly more complex problem. So here you have a network N that is a part of a bigger two-port network, and the Z parameters of this network is given to you, and you are supposed to find out the Z parameters of the complete network. So if the Z parameter, short way to find these to approach these kind of problems is the following. So what you have is, since the Z parameter of this network is given, so if you try to write the equations, what you get is the let's call this voltage as V1 dash, and let's call this voltage as V2 dash. So I1 you get as Z11 times V1 dash plus Z12 times V2 dash, and I2 you get as Z21 times V1 dash plus Z22 times V2 dash. So the voltage that is developed V1 dash. So this is basically the voltage across this Z11, and on in series of that voltage current controlled voltage source of Z12. So if I1 flows in this direction, there will be a voltage of Z11 times I1. Uh, okay, sorry. Mm, the this has been, sorry for this. I have switched it. So V1 dash is equal to Z11 times I1, and plus Z12 times I2, and V2 dash is equal to Z21 times I2, and Z22 times I2. I made a mistake and flipped the input and output parameters. Now, so what we have is, so this equation can be written in circuit form as mentioned over here. So if a current I1 flows in this branch, there will be a voltage of Z11 times I1 that is developed across this impedance, and the current that is flowing in the other port, that is I2. Due to that, a voltage of Z12 times I1 has to be added to whatever voltage initially was developed. So a resistance and current controlled voltage source in series will give you the port of the equivalent circuit diagram for one port. So similarly, we can do it for the other port. So we have a Z21 and Z22 impedance and current control voltage source Z21 times I2 as in series of each other, and this gives you the second port's equivalent circuit diagram. So this complete circuit diagram you can replace over here and then proceed with solving the question, and then it is a straightforward thing as discussed previously, that short circuit. So in case of finding Z, you have Z parameters, you have to open circuit one node and put a ideal current source in the other node, and vice versa. So yeah, from there it is a straightforward exercise. So now let's move to the final question. So in this question, there is a two-port reciprocal network, and on top of it, an additional 10 kilo ohm resistance is connected in parallel to it. So so when you apply 2 milliamp current in this network, you get a 1 milliamp current at the other port. Now, what is asked is what is the voltage developed across this 5 kilo ohm resistor if you apply a voltage source of 2 volts on uh, the initially output port. So what you can do is you can consider this complete. So you have a two-port network and a resistance in parallel to it in one port. You can consider this complete as a single two-port network, and then apply reciprocity, because you are adding a passive element to a already reciprocal two-port network. So the reciprocity will still hold. So what you will have is so since a 2 milliamp current is creating a current of 1 milliamp on the other port. So a 2 volt voltage source, a minus 2 volt voltage source will basically create a, voltage. So it will basically create a voltage of minus 1 volt on the other terminal. So now what is asked in this question is earlier, which was a 10 kilo ohm resistor, is now broken down into 5 kilo ohm resistor, and voltage developed across one of these resistors is asked. So you know that from reciprocity theorem, you know that the voltage developed across this complete 10 kilo ohm resistor will be minus 1 volt. So the voltage developed across one of the 5 kilo ohm resistor will be minus zero point 0.5 volts. So these were the questions from my side, and I have taken the notes, taken your feedback on current assignment 7. I will look at it and get the necessary action taken. So
Oh, okay, sir. Sir, this previous fourth, I think fourth assignment or fifth assignment, this digit problem, whether it is solved or not. So decimal precision regarding nearly 4 to 5 answers, we are not getting any mark for that.
understood.
Digit.
So
Mm,
uh, yeah. So what is the case is we there is a course instructor who coordinates the complete course, and there are two separate teams. One are the TAs for taking these tutorial sessions, and other are the TAs who go about the whereabouts of the uh, logistics of the course, the assignments and all. So
okay.
what we have intimated them, and they have taken it into account. And now uh, I I hope it since they have positively confirmed that yeah, we realize that this is a problem. I hope that that will, if it is not corrected till now, the final results will be updated with all the corrections made.
Okay.
So
Okay.
yeah,
Thank you.
okay. So thank you for attending.
Right. Right. Right.